Okay, a couple things. One is I handed out daily homework 12. It turns out it is not due on April 121st. It turns out that was too long of a due date for the homework to be turned in. I think maybe having it now due on maybe Tuesday would be fine. The other thing, it turns out that there were more than one typo on this thing. It turns out that there was a typo I made on the N3 up here at the very top. I do a lot of cutting and pasting, and I forgot to change this one here. And it turned out, you look at part C, 2 of the values here should have been divided by 5. Because if you tried working that out, you weren't getting anything close to that. It turns out now you will. Okay, so and since it is just kind of arithmetic, I don't think you'll find it very difficult. You need one for Denise? I can give one, maybe you another one.
Thank you.
You're welcome. I am in the process sort of starting to look at the test. I apologize for taking so long with that. You should, if all goes well, you'll be getting them back this week. We'll see how well that goes. So with that said, I want to finish up. We're going to get data today. Yay! We're actually going to look at real actual glass data. I've handed out the graph. Okay. Well, I want to wait till Ben gets here for the NMR. I know how he looks anymore. And so this is, I wouldn't want to problem that. The other thing is, just so you know, I'm probably not going to get through all the topics that I necessarily wanted to. So this, I'll make this open to everyone. I will probably over the summer, probably when I get back to Vancouver, start having regular classes on glass. So if you want to find out, if you want that information, come by and then you can actually get that. Obviously, there'll be homework that'll then go back and affect your grade. No, I'm kidding. I'll give out homework, but it's not obviously due. But if you just want to play with it, you can. Also, those classes will be recorded, so then you can look on them online. It'll be on basically viscoelastic theory. So I want to do, and I think that's something you should see actually kind of rigorously set up because it's used quite a bit. There's some little mechanical models that you'll see that are nonsense, but you're going to see them when you do research, and they're cute. They have kind of a fun quality. And then I think what I want to do as well is, and I've never done this before, I think I'd like to have then a section on Raman scattering, what that is, and go over kind of Raman spectroscopy, kind of set that up in detail. And then maybe even some stuff on NMR, because I know Ben loves NMR. So just what that is, how it actually works, but kind of set up some of the ideas in detail. I think I've been toying with this idea for a while, but now I think I'm going to try to go through that. I think I'm going to try to make this actually a 2-semester class, Physics of Glass 1 and Physics of Glass 2. Then I can get through all the spectroscopy in detail and everything, and then also the viscoelastic theory. And I still would like to do an extended section on green Kubo and some other stuff that you'll see coming up. And then I think between the two classes, I think you'd have a pretty rigorous development of glass. So, but there'll be some for the summer, so you can then still, for those of you who are here, large fraction of you are here, that'll still take care of some things. Okay, so that said, let's go on. So we're gonna do some counting today and get real honest data. Well, it's honest data. There'll be some data that doesn't agree with our theory, and then we'll find out what to do with that. Okay. Yes. And so that is showing up. Okay, so how did we start with this? We started off with Naumus. And what did Naumus do? He had a model for a system, which was what? What was Naumus' system? A collection of. Okay, he's a physicist. He has a collection of what? Harmonic oscillators. That's what a physicist is. And then he calculated basically the omega. So it was this D3R1, D3R2, D3P1, D3 all the way D3 to all of these here. He added those. He integrated all of these here. And there was a restriction on the sum. What was the restriction on the sum? Fixed what? Fixed energy. So the E was fixed. So the E was fixed to this P1 squared over 2M1 plus P2 squared over 2M2, 1/2 M1 omega 1 squared, delta R1 squared. He basically had the energy fixed. He did this, and then how did he then get the entropy for this? He said if you fix the energy here, you're integrating, your volume is fixed, this is nothing but a microcanonical. And so then the entropy, then this S is going to be this KB ln of omega. And when he did this, there were two big terms. Okay? There is one term here that depends on the number of large omega oscillators. And then there was another one here that depended on the number of low frequency oscillators. And so the way he, I'll try to make a picture of his paper here. The way it works is just take, imagine this is the x-axis and this is y-axis, and you have just one oscillator. If you had one oscillator that's like this, what happens? You have this shape here in this direction, quadratic. But you'd also have quadratic in this direction here. So it's kind of hard to draw. You could have something that looks more like something like this. But imagine now you have a frequency like this. Okay, so this is a high frequency, but you have a low frequency this way. What would that look like? It's going to look like a piece of paper like this. Because basically this direction here, we have a really, really, really slow curvature to it like this. And so that would look more like something like this. And what happens here, then you can have easy, if I had a shape like this, it'd be very, very easy for the system to kind of oscillate this way because the frequency would be low. And as a result, that's really going to dominate the entropy of the system. And so what we have here, and I don't have my little stuff here, this right here depended upon F. And what was this F here? This F was not the frequency, but the subtraction of small number of oscillators, small frequency oscillators. And how did that then affect everything else? How this affected everything is that we have this expression here. That if we look at the glass transition temperature, some composition X, and compare it to some sort of reference temperature, we know that this equals this. Here, this is from Adam Gibbs. So from Adam Gibbs, which I was just called AG, and the angel plot. We have this. And then what happens with this? Well, this is going to become this F at XR over this F at X. And what was F? Well, it's going to be this 3n minus number of constraints over n. And then this will be at some x of r. And then this would be 3n over n sub c at some x at n. And so what this gave us was the following. It's Tg at x, Tgxr equals 3 minus your n sub c. This is now, I'm calling n sub c over n, just n. Number of constraints per unit particle. And it's x of r. over 3 minus n sub gx. So we had those equations, and then we wanted to do an example of this. And we're going to follow this historically. And historically, what was the first example? That germanium solid glasses. Any questions at this point? So we're going to apply this to this germanium X selenide 1 minus X glasses. We said the nice thing we like about these glasses is that they form a glass over a wide range of compositions. And what did that mean? The X is going to be worth the maximum value of X we're taking 2/5. Oh, and I did ask Celia if you would proctor the exam for you. He said yes. But I said, just make certain that you only give them answers in the form of Russian. So you can ask him a question in English, but he'll only give you an answer in Russian. Okay? But you'll have a puppet to help translate. So that'll make life good. Okay, so you have to work for any type of thing you ask about you. Okay, what are we doing? We're doing this. So, yeah, these GEX, SE, 1 minus X are good glass forms.
Yeah.
In the range. And what did we say if we have X equals 0? If X equals 0, it is pure selenium. This is pure selenium. What did we say selenium looks like as a glass? Long chains. Okay. So pure selenium glass is basically long chain. They're double bond. Each selenium atom is double bond. So you get these really, really long chains. Okay. And again, this is what John did for his PhD thesis. He actually developed really good chalcopyrite potentials. He did other. I was on his committee. There's a lot of stuff on his thesis. He developed very accurate. Okay. Now, what did we say happens at this 2/5 range? If you have pure this, right? We put in the 2/5 here. What is 1 minus 2/5 called? 3/5. We said that this is just our GE2, SE3. Well, what did that little thing look like? Try to say draw this. Looks like P2 was 3. Okay, so it looks specifically like. We have a double bond there, and then we had double bond. We had selenium coming out. Okay. But there's a complication in this class. What was the complication? Set of X equals a third. However, X equals a third. We get to do more math. We get GE a third. SE 1 minus a third. Okay. Oh, 2/3. Oh, there's a joke from high school. Third reminded me of it. Remember, this is high school, so it's high school humor. What? Tree and a third plus a tree and a third plus a tree and a third plus 10. Okay, I did mention that this was high school. I think, I mentioned it was high school. Okay, maybe middle school. Okay, back to this. Okay, so then we had this GE a third, SE 2/3. This was your GE SE 2. Now this was just like what? This looks like SiO2. I'm going over these because we need the structure order to apply these ideas. Okay, so these look like this. So an x equals a third looks like SiO2. These tetrahedral like this. Okay, that's what you have. But now, what happened if we set her if we're in this range here? What did we say happens in that range? Yeah, we're going to get these fellows are here. But now we're going to have really, really long chains of selenium connected. This range here, we have these little fellows like this. And these can be connected to really, really long chains here than connected to more GPUs. So this is going to break into two regimes. It's going to break into this regime here. And then it's going to break into this regime. Makes sense? So in this case here, we're going to have a combination of basically these guys, and then also these guys here. What we did is that we wrote these out. So this guy here, we said this is the same thing as G. So this is the GE SE2. We had X of these. And then this was SE. Was this 3 minus X? 3X minus 1? What, 1 minus 3X?
1 minus 3X.
So we said this is how we can write this regime here, and then in this regime here. That became this. What was this again?
X.
This is X?
Yes.
No, I don't think so.
2 minus 5X. Yeah, 2 minus 5.
2 minus 5X? And then this was
2 minus 1.
3X minus 1. So that's what we had last time. Okay? That makes sense? Kind of a long introduction, but long weekend as well. Now let's go through and count. Let's actually apply our theory. So what it means here is that we're going to actually have to apply this in kind of 2 separate cases. One over here, then one over here. And I think in this sheet over here, what we're going to do is take this sheet. We're going to get back to it in a bit. We're ultimately going to derive these expressions here for F of this equation 39. Okay. So let's do this. So let's apply our theory. To these guys. This is the first thing we have to realize is that in this theory, the constraints. Various constraints. Set in at different temperatures. So what kind of constraints do we have here? Again, think of this as just being kids' toys. So what kind of constraints did we say we could have? Linear constraints, angular constraints, and we could have other things too, but we're going to assume that these are going to sit in a different temperature. So let's assume that different constraints. Let's say linear bond. Also say linear and angular. Set in at different temperatures. Okay, the one that sets in first we're going to call alpha, the one that sets in second we call beta, gamma, delta, so on and so on. Okay, so call. I don't like that part because when I think of alpha, I always think of linear bond constraints. In this case here, the alpha may not be linear bond. It's going to be whatever sets in first. That's what's alpha. So call the first constraint. That sets in alpha, followed by beta, gamma, delta, so on and so forth. For some reason, we didn't use epsilon. We then kind of go to lambda. I don't know why we did that, but it should be epsilon. But it turns out that we're really going to get past the beta. We'll see why. Okay. So why do we do this? So let's look at the number of constraints. For this right here, and this range right here. What kind of constraints? We're going to say for each GE atom. Okay, how many angular constraints should there be? In this regime here, what do we know about GE? When you do this theory, one thing you need to know the structure of the system. So when we said in this regime here, what do we have? Yeah, we have these fellows here. Don't better know. So what kind of constraints do we have setting in? Let's start with angular bond. So what's the coordination number for my buddy germanium? 4. So what's our handy dandy formula for calculating the number of bond constraints? Angular bond constraints. 2 times the coordination number minus 3. Okay, so the number of linear bond, the number of angular bond constraints. And this is just a good thing to know. It's going to be 2 times the coordination number. I'll just say C sub n. I'll take out that bracket. 2 times the coordination number. Is this actually showing up? It's really faint. I will turn to blue. Blue won't let me down. Ooh. Minus 3. So for this case here, what do? We have 5. Okay. So for each germanium atom, we have 5 SE, GE. Well, I'll just say 5 angular lengths. Now, how many GESE linear bonds then do we have? 4. But what do you know about these bonds here? They're shared. Okay, so we're gonna have 2 of those. Okay, so we have 2. We have a half times 4 linear bonds for each GE element. Now, what about selenium? Okay, if you look at the selenium here, the selenium is like this, 4 selenium. Okay, what did we say about selenium? Selenium is this guy here, right? So what's selenium's coordination number? 2. So the coordination number for selenium. I should put this over here, coordination number for GE. So how many angular bond constraints would I have then for SE? Okay, angular bonds.
1.
2 times 2 minus 3 is 1. Now, how many then linear bonds then would I have for each selenium atom?
1.
One of those is true. Yeah, right? You have 2, but then you have to take half of that. You're gonna have 2 times a half, well, half times 2. Let's write that down. Nice. So the number of angular bond each SE atom is 2 times 2 minus 3, 1. The number of linear bonds. One half to 1. Now what we have to do, we have to rank these things. We have to ask which one set in first. Now this is something where this is not always obvious. You have to do it from structure to structure. And so that's where this is, it gets a little tricky to do. It turns out that normally what would you think would set in first? Yeah, I would argue the linear bond would set in first. It turns out it does not. It turns out the angular bonds in this case are going to set in first. Maybe they don't, maybe they do, but the NMR data clearly shows I don't know. The angular bond won't set in first. So the angular bonds for GE SE2 set in first. Okay. Notice these fellows here are not setting in first. Okay, it's only those here. And how many of those do we have? How many of these constraints do we have? 5. We have 5. Now, how many germanium atoms do we have? X. So if I look at the number of constraints per atom here, I'm going to have basically X. This is the number. Again, this is a fraction. These are fractions. This is what I can do. The number of the fraction number. Of GE is this. And then the 5 here, this is number of angular constraints. But now what's going to happen? And then what we're going to have, then we're going to have plus other constraints. I want to illustrate the problem with this guy here. Now, if the temperature is really, really high, what are we going to say then about the number of constraints if the temperature is really, really high? We're going to say there's no constraints. As you lower it, this term is going to appear. So how?
Is that 5 multiplied by the x or?
Yeah, I'm putting the number here, then the 5 here. No, you would never write it like that because it's like stupid. Okay, so we're going to put the 5 here, but the way I set it up here, I put the x, the number, then the number of constraints. But this is the way I've written it. It looks stupid.
Okay.
And then I'll leave it like this because we're going to add something on here. So how can we modify this equation to be 0 if t is large, but 5x, I'll keep the same form, x times 5 if the temperature is below some critical value. Critical temperature, call it T alpha. Why am I going to call that one T alpha? Because in this case here, the first one setting in is the angular bind constraint. So we call that then one of the alpha constraint. Okay, fine. So I want this for a large temperature to be, I want this to be 0 here. But then for a low temperature, I want this to be 5x. I'm going to multiply this by something which is either 0 or 1. This is how we do it. This is actually going to be, and you may have seen this in our classes, this is going to be a Heaviside step function. Okay. So to do this, mathematically, we use a Heaviside, and okay, I don't know if you noticed, but spelling's not my strong point. Okay, just FYI. I am spelling his name correct. Heaviside. He was actually an electrical engineer. So you know when you look at Maxwell's equations, you have this notation like this. And like this. This notation here. He came up with this. Maxwell actually had this really, really awful stuff. So all this notation here, the divergence and stuff like this, he's the one who came up with this Heaviside. He was an electrical engineer. He came up with that. He had scarlet fever as a boy, and it affected his hearing. And I think it also could probably distance himself from society. He ended up just having a really rotten life. He ends up taking the furniture out of his house and replacing it with stones. He kind of walks around with stones in his house. It does not end well. It does not end well.
Well, I think that it's maybe behind me.
And a lot of that stuff he actually taught him. He was going through. It's a Maduro poor family, and if you go through his family was able to educate him up to a point. Then after that, like 16 or 15, he was basically self-taught. And people realized right away what he was. There's just going. Okay, this is going to be the following function. It's going to be a capital theta, and it's capital theta. And what this is going to be, it's going to be a function of x. And it takes on one of two values here. If x is positive, it's 1. If x is negative, it's 0. Now, just so you know, you could say, well, what happens if it is equal to 0? Well, then people take it to be a half, but I've never used that value, so we're not. So if you're going to make a graph of this, hey, why is it called a Heaviside step function? It's going to be 0. It's going to be 0 here. Then it's going to be 1. So what's something like this look like? What would then this be? Try to say graph this. Let's graph this one. And then let's graph this one. Capital theta. No.
Show me why.
Can Calvin make that letter? Okay. Should we add that to the board? The board's gone?
Yeah.
Why? Too many things?
Diagrams.
Okay, so how do these look? I'll give you a hint. Here's 5. And here's 5. It's like I gave it away. So for what values of x is this positive? For what value of x is this positive? So this will be 1. If I'm over here, is the argument they're positive? Yeah, so this is going to be 1. 1. It'll be 1 here. If I'm over here, what happens?
0.
This is now negative, and so this is going to be 0. What about my buddy over here?
0 and then
That's going to be this guy. And then
1.
this one. That's what that looks like. Okay, how many people know what a direct alpha function is? 1, 2, 3, 4, 5. Okay. What would happen if I differentiate this? You'd have 0 here. You have 0 here. At this point, you get a spike. So the derivative of these are actually direct alpha functions. So that means nothing to do. Don't worry about it. You're going to be doing them later this week. So what can we do with this? This is how we can use this. We're going to say the constraint is either on or off. Either the strain is there or it's not. So what that means here is I can say that the number of constraints is going to be x times 5 times theta. And I'm going to write this as T alpha minus T. Now I'm going to start just making a regular theta because I'm tired of writing this stuff here. Sorry for changing notation. I can make it. So what would happen if T is large? If T is really large, this argument is 0. So I have no constraint. But if I lower this temperature below some T alpha temperature, where I'm saying that those angular constraints come in, this then is 1. So I can put this in here. Okay. But hey, that was so much fun. Let's put in the linear bond constraint. So I'm going to say that the linear bond constraint is going to come in at some lower temperature. I'm going to call that beta. So we're going to know how to put some constraints. Now, let the linear bond constraints come in at a lower temperature. Call it, what would we call this temperature? T beta. Yep.
Is the X multiplying the entire?
Yeah, this is going to be, I should end it, go like that here. Then plus other constraints that we don't know. That was bad for my hand. Okay. So we're going to call this T beta. Okay. So now what happens to our little expression? Now we end up with this number of constraints. It's going to be X. So the number of remaining minutes we have. Times, call this 5 beta T alpha minus T plus Then you tell me what the next term will be. What did we say about the number of linear bond constraints that the GE atom has? 2. So what will I then put in for this? 2 capital theta. Theta. That makes sense? Okay. Now, what about this selenium? There's 1 minus x of this. What can I do for the angular bond constraints for selenium? I could say that they're coming in at the same temperature. Maybe they're coming in at a different temperature. I don't know. And I have to check the paper to see which one it is. I think that we said that they're coming in at the same temperature. Like, I reserve the right to change this one here. Okay. What would that then put in for this? So how many? We said the number of angular constraints for the selenium is what? 1. So this would be a 1. If it's coming in at the same constraint here, the angular constraint, this would be this guy here. So this could be minus T here. This may be a T alpha here. It might be a T alpha. Or what can I say? These are going to set in at some different temperature here. And this would be then a T gamma. What would determine which one we put in? Yeah, so this one, what we're saying, this is going to be the angular constraints for the selenium. This is going to be the angular constraints then for the germanium. Maybe they come in at the same temperature, maybe they don't, and you don't really know until you kind of tinker with the steps. Okay. Now, what else do we have though? I could then have the linear bond constraints, and how many for these? 1. And I could say, what can I do? I could say that those are coming in at the same temperature or at a different temperature as well. So I could have is then, so this is angular constraints. For selenium. And this is going to be the linear bond. Like I said, this is going to be 1 here, theta. I could have here is I could have new value, new Greek letter. Or I could have, or I could go back to my beta. Have something like that.
Minus T.
Keep me honest, okay. And then what do we say also happens? The selenium has what? Really, really long chains. Okay, if I have a really, really long chain of selenium, really, really long chains of selenium, what can these chains do? There might be some sort of van der Waals interacting. So what I could also do, and I'm just going to say there's 1 constraint for all the chains. I can say, excuse me, thank you. I'll just put this in here like this. This would be T new temp minus T here, and this is going to be for the van der Waals. Constraint. So let's start cooling this system, see what's going to happen. I'll get to one of the spots here, and we'll call it good. Okay. Does that make sense? So I think this is actually going to be a different, I think we're going to call this one T gamma here. So let's assume. Let's call this T gamma. I'll look in the paper to see what it's actually. I think it's T. Let's start seeing what's going to happen. So if T is greater than T alpha, what is our N sub? What is N sub C? Zero. So our F, which is 3 minus NC, is 1. 3. Not very hard. Okay. Now let's try the next one. If T is less than T alpha, greater than T beta. Succeed. Yeah, this is 1. I get a 5 times x. So it's 5x. Okay. If this term contributed, if this was a T alpha, what else would I have? Then yeah, plus a 1 minus x here. If I take this to be different, and let's say it's going to be something, let's say a lower temperature than that, then this would not kick in. So we're just going to say that there. Okay. So what is my f then? This is 3 minus 5x. So let's just stop here and figure out what the TG would be then. What would TG x be for this temperature? How does our little handy dandy experiment go? It's going to be TG at x equals TG at some reference point equals F at some reference point over F S of x. Well, we're going to take the reference point to be 0. So left XR equals 0. Get this one thing and then we'll call it good. Then we'll finish it up tomorrow. So if I were to put in the 0 here, what I got? I get TG of x over some TG of 0. So what kind of glass am I putting in here? I'm putting in pure selenium glass. Okay. Equals. Okay, when this is 0 here, what is going to be the number of constraints? And this temperature range? 3 here. Sure. Okay. This is just going to be our 3. Right? You can see it from here. When I put an x equals 0 here, this just gives me 3. Okay. Over 3 minus 5x. So what does this tell me? Clean this up to make this at 1 minus 5 times x. This TG of x here is going to be TG at 0 over 1 minus 5 times x. It turns out that that value actually works. Okay, there. And that actually agrees with the data. Okay. Now, in which range of x is this true? This is going to be 0. Okay. Pretty slow. We'll do more of these on tomorrow. And there's something, I don't know, very Sudoku like this, but kind of easy Sudoku, because you just keep on adding more terms and you work out your little algebra. And you do 3 minus your little algebra. Cool. Have a good day.